Registration
thank you.
start? Okay, that's perfect. Okay, so good morning. As I told you before, my lesson will be about dynamics of lava, magma eruption and related deposits, especially lava flows and lava domes. So, sorry. Okay. What are the, I have to switch. Okay, these are the outlines of the lesson. I'll mostly introduce, give some brief introduction. Then I'll talk about the physical properties and composition of magma. I'll talk about the rheology, the products of effusive eruptions, introduce the principal type of volcanoes, and then I'll give some examples of historical lava effusive eruptions. So what is a volcano? A volcano is a very complex geological structure generated within the earth crust by the rise following the eruptive activity of a molten rock mass that formed beneath the earth's crust. The generic volcano is made up of a magma chamber, which is the underground reservoir where the magma that feeds the volcano is found. Sorry. Okay. Good afternoon. Okay, so the main volcanic conduit where the magma passes to rise from the magma chamber to the surface. And then the crater or summit vent where the main conduits flows. And then there can be also one or more secondary conduits which give rise to lateral vents or eruptive fissures. So depending on the lava chemistry, especially the amounts of silica and dissolved gas, volcanic eruptions can be divided in explosive and effusive. So if a lot of gas is trapped in the magma, the pressure will build until the magma erupts explosively from the volcano. You can think to a soda bottle, for example. If the gas is trapped in the liquid, but if you shake the bottle, the gas wants to come out from the bottle. If you remove the cap, the gas comes out together with the fluid which is inside the bottle. Conversely, an effusive eruption rise when the magma has a low viscosity, so it's runny, and a small amounts of gas. So it produces an effusive eruption with lava flows. So, in essence, what we can see is that the occurrence of when explosive or an effusive eruption depends on the physical and chemical properties of the magma that feeds it. Okay, so what are these physical properties of the magma? Please, if you have. Good afternoon. Please, if you have some questions, if you want to ask something, please stop me. I'll see you. Okay, so what are these physical properties of the magma? These the physical properties depends on these four characteristics, which are the chemical composition, temperature, density, and viscosity. The chemical composition refers to the type and amount of minerals and gases that are present in the fluid. Temperature, as you know, magma is very hot, with temperatures that can range from 700 to 1,300 degrees. Obviously, the temperature depends on the chemical composition. So the magma, which is more silicate rich, has generally lower temperature that are with respect to those that have a lower silica content. Then the density. Magma is less dense than the surrounding rocks, and for this reason it can rise to the surface. However, the density of magma can vary depending on its composition and temperature. So I can see that all these characteristics are all interconnected. And finally, the viscosity, which is a measure of the resistance of a fluid to flow. So magma has a high viscosity to the high content of silicate minerals and dissolved gas, which make it sticky and thick. So let's do a first classification of magma. Based on their composition, magmas can be classified into three main categories. Mafic magma, which is also called basaltic, have a silica content between 45 and 55%, so has a lower viscosity and erupts at higher temperature between 1000 and 1200 degrees. And generally, due to these characteristics, they produce non-explosive eruptions with fluid lava flows. Then there are intermediate magma, which have a moderate silicon content between 55 and 65% with a moderate viscosity and intermediate temperature between 800 and 1000 degrees. And finally, there are felsic magma, also called rhyolitic, which are those with a higher silica content, more than 65%. So they are highly viscous, and for this reason they erupt at lower temperatures between 650 to 800 degrees. And for this reason, this magma tends to produce highly explosive eruptions. Okay. Any questions? No. Okay. Let's talk about the rheology. When talking about lava and diffusive eruptions, it's not possible not to talk about rheology. What is the rheology? Rheology is a branch of the physics that studies how. Sorry? The question? Okay. So, rheology is a branch of physics that study how materials flow and include two main properties that are the viscosity and the yield strength. Viscosity describes how fast something flows, while the yield strength if something flows. So, viscosity. Viscosity is the resistance to flow, so is the opposite of fluidity. And it's a property of a substance that relates a known amount of deformation, for example, a steering force, to the rate that the substance deforms or flows. So, namely, it describes how fast something flows for any given amount of steering. For example, water and oil obviously don't have the same viscosity. For example, we can make an experiment. If you, for example, have a bowl of water, and if we push with a certain force on a spoon, the water will begin to flow very fast. If the bowl is full of oil, the same force on the spoon produces slower movements with respect to water. This demonstrates that water and oil have a different viscosity. So if you want to have the same velocity in the bowl of oil, we have to put a higher pressure to the spoon. How viscosity can be represented? Since it is a function of the deformation rate and applied pressure, we can represent it. We represent by making in function these two characteristics. For the same applied fluid, what we have, for example, let's see this graph. For the same applied pressure, we have a low strain rate for the fluid having a high viscosity, and a high strain rate for the low viscosity fluid. Or we can say that in order to have the same strain rate in a low viscosity fluid, we have to apply a higher, a stronger pressure. I don't know if I've been clear. Okay. So this is the graph of three different substance with three different viscosity. So low viscosity with the low applied pressure needed to deformate, and a high viscosity fluid that need a higher applied pressure to move. But let's see what is the yield strength. What is the yield strength? Yield strength is another important aspect of rheology, and indicates how hard you have to push on a fluid to make it flow. For many fluids, gentle pushes do not produce any movement. So there is a certain amount of force that should be exerted on the fluid before it flows. This certain amount of force is called the yield strength of that fluid. Then, once the fluid starts moving, the rate at which it moves is a function of its viscosity. So the yield strength is not a property of fluid. For example, water doesn't have a yield strength. So no matter how gently you push, the water will move. Therefore, water, like other fluids, for example, chloroform, ethyl alcohol, don't have a yield strength. These fluids are called Newtonian fluids. So, yield strength, if you want to represent the yield strength, we can represent it as the applied pressure versus the strain rate. And this is a graph representing two hypothetical non-Newtonian fluids, which are called Bingham. As you can see from the graph, the lines doesn't start from the origin, so they don't start from zero. These values is the epsilon, the values of the epsilon intercepts defines the yield strength. So the fluid B, for example, has a low yield strength, so it can move in a time. It can move with a small pressure with respect to the fluid A. So for fluid B, an applied pressure that is less than the yield strength of fluid P doesn't produce a deformation. The same thing for the fluid A. So the values of the epsilon intercepts define the yield strengths, while the slopes of the lines represent the viscosity of the fluids. Is it clear? Okay, perfect. Okay, what is lava? Lava is a typical Bingham fluid. So it has an yield strength and then a viscosity, which can change depending, we will see from the type of lava. But we can say that lava is a typical Bingham fluid with an yield strength that is between 100 and 100,000 Pascal. Okay. What are the products of effusive eruption? Lava and magma are two terms that are often confused. So someone talks about magma and lava referring at the same thing. It's not so, because they represent two different geological phenomena. While magma is the molten rock beneath the Earth's surface, lava is the same molten rock once it reaches the surface. So magma is below the Earth's surface and the lava is on the Earth's surface. Okay. The flow, a lava flow can be characterized by extremely variable shapes and dimensions, which mainly depend on these parameters. The effusion rate, which is the quantity of magma erupted in the unit of time, the physical properties of the magma, and the topography, which represents the ground steepness. So depending on whether a lava flow is erupted in a subaerial or underwater environment and on its chemical composition, obviously it can have a different aspect, a different morphology, different external characteristics, let's say. Lava flow types or morphologies can be divided in these 6 classes. Power oil, AA, blocky lava, pillow lava, sheet flow, and lobate. The third 3 refers to the lava flows that are subaerial, so on the Earth, while pillow, sheet flow, and lobate to subaqueous eruptions. And now we'll see what are the characteristics of this lava. Pyoe lava. What is pyoe? Pyoe derives from the Hawaiian verb that means oe, so to row, since oars create eddies in the water. Indeed, as you can see from the photo, these lava flows are characterized by smooth, wavy, and roped surface. For this reason, Pyoe lava is also called rope lava, because its appearance resembles that of a rope. This particular appearance is due to the fact that the lava is very fluid, generally very fluid. so solidifies on the surface but continues to flow quickly underneath. Power lava we'll see that are the analogus of pillow lavas in submarine eruptions, and depending on the appearance, they can be classified in different POE, which are, for example, shelly, scaly, entrail, reticulous core, and so on. So the main characteristics is the low viscosity, hot temperature, and fast-moving lavas. These lavas, okay, this is, no. Sorry. Let's see if I can share you the video with another, this one. I want to show you this video because it's very beautiful. Okay, sorry, I'll switch off this one and do, okay, and okay. Because I want to, okay. This is a video of a power lava, in particular during an Icelandic eruption in 2021. As you can see, these eruptions are very calm, with characterized, indeed they are highly fluid basaltic lavas with silica content less than 55%, with a speed rate that goes between 10 and 100 meters per hour. The main characteristics of this lava is that is made up of overlapping globes of lava that are called lobes. And these lobes formed by breaking previous ones, so the incandescent lava flows by overlapping the coldest globe. So these, as you can see, these lobes, when the new lava with new more molten lava is injected, they become to inflates, and then the lava breaks the skin at the marching, creating the next slope. And the characteristics of this lava obviously can change depending, for example, on the steepness, velocity, and viscosity, and this can transform power lava into AA lava. So AA lava means burning, fiery, and is characterized by this. As you can see from the photo, it is very different, the appearance of the lava with respect to the pyro lava. It is characterized by irregular, fragmented, and scoriaceous fragments that are called clinkers. These on the surface, generally the upper surface cools and becomes rock, that are continuously ripped apart by the moving molten lava inside the flow. The characteristic of this lava is that after cooling, they become a jagged block that it is very difficult to walk over without stumbling and getting cut. So the characteristics of this lava is that the high viscosity, that is a cooler, the cooler temperature, and the slow moving. And this is a video of Etna in December 2022. As you can see from the video, the movement, the lava flow emplacement is very different from the lava. The clinkers are visible, and the characteristics are very different. For example, the speed rate usually doesn't exceed 1 kilometer per hour. With 30 kilometer per hour, the known velocity of an lava. And another characteristics of this lava is that it flows mainly flows in channels. An increase in viscosity due to crystallization or cooling can cause a transition to a lava to blocky lava. Okay, blocky lava. I'll share this. Okay, blocky lava is the last one for subaerial eruptions. Okay. And this kind of lava forms in more viscous lava flow with a silica content higher than 55%. Block lava flows have surfaces with large clusters of loose angular and smooth or curved blocks, but these blocks are different from those forming in lava because they are more massive and less angular than the clinkers. They are the slowest ones because their speed is generally less than 1 kilometer per day. And their cross section has a rubbly top, then a massive core, and then some buried rubble that fell on the leading edge of the bottom. Pillow lava. They are composed mainly of basaltic lava. They are like spherical or pillow-shaped mounds, which are generally associated to eruptions, submarine eruptions with low discharge rates, so low effusive rates. Even if they can form also in lakes, under the lakes, or in oceans, like in Hawaii. The dimension of these pillows goes generally between 10 centimeters and 1 meters, and form irregular mounds, which are stacked or interconnected rock masses. The surface are smooth and striated, as you can see from the photo. And the characteristics is that some of these can also have these finger-like protrusions that seems a hand. And they are mostly crystalline due to the slow cooling rates. Sheet flows. Sheet flows are eruptions with some subaerial lava flows, but also but also submarine lava flows, but also submarine lava flows that spreads like thin or thick sheet of lava. These have a thin glassy crust with the surface that can be smooth, stringy, ridged, grooved, folded, spiral-shaped, or messy. And they are similar to the PIOE, but the main difference is that that is not tube fed, but is sheet fed. It forms from high discharge rate fissure extrusion with highly fluid lava. Lobate has these elongated flat lobes and with smooth glassy rings. The surface have these local depressions with the individual lobes, which are cold but firm. And the shape of the structure of lobate lava is similar to those of pillow lava. Indeed, someone says that they are considered as a variant of pillow flow, even if they are extruded with either fusion rates. Many volcanic fields in submarine eruptions can form a pillow, sheet, and lobate flows, with lava having the same characteristics, the same chemical composition. So the composition of the magma doesn't influence their formation. What influences is mainly the discharge, the diffusion rate, the pre-existing topography, the viscosity, and the flow conditions. For example, a decrease in discharge rate can transform a sheet lava to lobate and eventually to pillow lavas. If you agree, we can. It's. I don't know. We can go until other 5 minutes, and then we can have a pause. Yes, please.
Okay, in our region, we got some columnar lava. And so what about viscosity? What about this phenomenon exactly? Because I know that is subaqueous, but I cannot relate it with pillow, sheet flows, or lobate.
No, maybe they are. It depends if they are. Because these kind of eruptions are submarine eruption. They are not subaerial eruptions with the lava flows that goes inside the sea. This can be another phenomenon. I don't know what kind of what volcano you are referring. If you talk about subaerial eruptions with the products, the lava flows that reaches the sea and goes through the sea, or you are referring to submarine eruptions, so eruptions that occur from volcano under the sea.
Okay, I understood. So no, in our case, the eruption is subaerial, but the lava reached not the sea, the river, actually a river.
Okay, the river. Okay. So it cools. It cools when it reaches the river, and it has this kind of shape. Yes.
Thank you.
You're welcome. If you agree, out of 5 minutes, and then we can have stop a coffee break. Are you tired? Do you want to stop now? Okay, let's see very quick some characteristics of lava flows. One of the most important factors that influence the forms of lava flow is probably the effusion rate, which is measured in cubic meters per second. The higher the effusion rate, the greater the distance traveled by the flow before stopping. When the lava flow, the effusion rate is very high, generally the lava flows tend to be composed by a unique cooling unit, so they are called simple flows. While when for low effusive eruptions, they tend to form different cooling units that are closely together in time, so they can overlap, and these are called compound flows. So compound flows are those lava flows for which lavas can be divided into flow units, while simple lava flows, the flow is not divisible. Now we will see some characteristics, some interesting phenomena due to effusive eruptions, which are lava lakes and lava falls. Lava lakes, okay, it is not usual that lava accumulates into volcanic craters, filling the craters and generating what are called lava lakes. If the fusion rate is constant and high, the lava may rise above the crater rim and produce overflows, so the lava that goes through the flanks of the craters. If the topography is very irregular, and especially it is the terrain is very steep, it can also produce lava cascades or lava flows. In figure, we will see the lava lake in Kilauea, Hawaii, and the eruption of also in Hawaii of 1969-1971. Lava tubes. Another important phenomenon, which is very important from the hazard point of view and from the risk mitigation associated with the effusive eruptions, are lava tubes. The chilling and crystallization of basaltic lava around the sides, bottom, and on the top of lava channels can produce this sort of rock encased conduit, which are called lava tubes. This phenomenon, as I told, is very dangerous, because the surrounding lava cools and insulates the interior lava, which is relatively hot, and it's prevented from further crystallization. So the lava continues to flow inside the lava tube with very high temperature. An example, Tet9, for example, in 1971 or in 1991-1993. These lava tubes can be very different from both in the width and the length. For example, they are typically less than 1 kilometer long, but there are also, but there are also lava tubes in Australia which are more than 100 kilometers long. Also, the width can be very different from less than 1 meters to more than 15 meters. But as I told before, the main hazards linked to these volcanic structures is that it represents an efficient mechanism for basaltic lava flows to reach greater distance from the lava vent without losing it. So the lava inside the tube continues to flow at very high temperature, which are even more than 1,000 degrees. Okay, tumuli. Tumuli are formed forms when the lava flow reach flat or gentle slopes. Lava flows that are slow moving. So when the lava reaches these gentle slopes, becomes too cool, form a thin crust, even if under the crust the lava is still viscous and molten. So the lava starts to push the crust, which rise up like a bubble. This can have tumuli can be like steep-sided domes, or have a more elongated form. In this case, like on the right, they are called pressure ridges. These are two examples of tumulus, one in Australia and one of Palo lava due to eruptions in Hawaii. Okay, before starting with the principal types of volcanoes, we can have 15 minutes, 10 minutes of stop. We can have a break. Okay. Okay, let's see at 5:30. Okay. Okay, in 10 minutes, more or less. Okay.
Okay.
Okay. Okay. Thank you.
Thank you.
Okay, thank you.
We wait for your colleague that was here before the break. 1 minute and then we start again.
Maymun belki. Hi, it's hi. Hi. It's hi.
Hi.
Hello.
Ciao. It's not so easy for workers with children in the afternoon.
Indeed.
I have one at school and two that are sleeping upstairs. I hope that that will sleep until the end of the lesson. Okay, let's start so we can have 10 minutes at the end of the lesson for questions. And okay, so what are the principal types of volcanoes? This is the first classification, the main classification of volcanoes in cinder cones, composite volcanoes, shield volcanoes, and lava domes. Okay, cinder cones. Cinder cones, which are also called scoria cones, are the smallest, simplest, and most common of volcanoes in the worldwide. These are cones that forms by the deposit of the eruptions and by pyroclastic fragments formed by explosive eruptions or lava fountains from typically from from a single cylindrical vent. And these so the lava, the fragments of lava accumulate around the cone, the vent, forming this conical hill, which has a ball-shaped crater on the top. And composite volcanoes are large volcanoes which can be which can be many thousands of meters tall. They are larger, steep-sided and cone-shaped the volcanoes. They are formed by very viscous and slow lavas. And for this reason, the lava doesn't flow very far before solidifying. These volcanoes are also called stratovolcanoes because they are composed by alternate layers of ash and lava. They are generally active over long periods that goes from tens to hundreds of thousands of years and erupt periodically. They are produced generally by violent eruptions, and these are two examples like Mount Rainier in USA and Volcán de Fuego in Guatemala. Then shield volcanoes. These are large volcanoes with gentle slopes, as you can see from the photo. They are the largest volcanoes on Earth, but they don't have the typical conical peaks of volcanoes. Okay, which we usually call the volcanoes the mountain. Okay, they don't have this conical form like composite volcanoes. Instead, they are broad volcanoes with these gentle slopes, and they are called shield volcanoes because they seem like a warrior's shield resting on Earth. And they have a convex shape because they are flatter near the top. They are produced by less violent eruptions. They are not formed by, they do not have a layered shapes, like they are built almost exclusively of lava, and they are usually constructed by basaltic or andesitic lava flows, which are very fluid. And these are two examples in a way, the Mauna Loa and the Kilauea in a way. Then we focus on lava domes. So what are lava domes? Lava domes are very characteristic eruptive structures. They are a lava dome is a volcanic edifice that forms when the lava that reaches the surface is so viscous that it's not able to flow away easily from the vent, so it accumulates around the vent. So the composition is typically andesitic to rhyolitic, and they form commonly when there is a small initial extruded mass of lava, which gradually expands due to new lava coming from the bottom, from beneath. So it is forced upward by the interior. The solidified shell can form fractures that and small flows of lava can flow, but this lava is extremely viscous. And the characteristic of this lava being very viscous is that it is emitted at low temperatures between 600 and 800 degrees. So what happens is that the gas accumulates and can influence the rupture process of the lava domes. So, moreover, if the lava domes grow very quickly, they can become structurally very unstable. So this is the main hazard to this kind of eruptive, this kind of volcanic edifice that can be very dangerous for people, for areas near the volcano, because the gas inside can produce explosive eruptions with the collapse of the dome, and thus the formation of pyroclastic density currents that are flows of very hot materials which can travel very fast from the lava dome. Okay. Lava domes can be classified in different ways. This is a classification based on their morphology from Blake 1999, based on their shape, texture, and eruptive styles. But in this case, based on the morphology, they can be divided in low lava dome, Pelen, Poulet, and upheaved plug. Okay, low lava dome are also called torta due to their similarity with the cake. They usually erupt on a very flat terrain, and so the lava is not able to push outwards. Is able to push outwards, but not far from the emission center. They have a shape which is usually flat and almost circular. For this reason, they seem a cake. This is the thickness and diameter of these domes can be very different from a few meters to nearly a kilometer, and can be also several kilometers in diameter. They grow through internal processes with the lava that fills the center of the lava dome near the vent, and pushes outwards the older layers. So inside they have an onion-like structure. The Pelian lava domes have been named after the iconic lava dome which formed in 1902 in Mount Pelée, which then caused a collapse that destroyed Saint-Pierre in Martinique. And these have a circular shape as tortas, but they don't have a flat top, but they have this kind of tall vertical spins, which are characteristics of the Pelian lava domes. They have this steep shape that, for this reason, they can be very dangerous due to the hazard to collapse. Cooley lava domes. They are sort of they are between the low lava dome and the lava flow. Because they don't flow. They are similar to lava flow, but they are not able to flow more than few kilometers. They typically form when the lava is very, very viscous and is extruded down the steep flank of a volcano. They have an elongated shape that generally is not so long than few kilometers, that spread along the slope of a volcano. And the characteristic of these lava domes is the ogives, which are these pressure ridges that you can see on the figures on the bottom, which are characteristics of the surface of the flow. For example, Chao, which is the Cooley lava domes in the Andes, is an example of Cooley lava dome. As you can see, it was eruption on a very steep slope, which allowed the lava to flow almost 14 kilometers from the downslope. And this is a photo of this interesting volcanic structure. And finally, half-heaped plugs, which are very rare and interesting type of lava dome, because the lava, with respect to the other lava that generally form the other kinds of lava dome, the erupting lava of the half-heaped plugs have higher yield strength, so they are stronger. They need more pressure to flow. So the result is that the lava is pushed up like a piston. And these piston-like extrusions often can travel very high above the surface and can also carry country rock sediment along with them, and that can be found on its upper side. This is an example upheaved plugs in Japan, the Usu stratovolcano, that formed these upheaved plugs on its eastern flank. And on the right, you can see, since the eruption of this volcano occurred, this dome occurred during the Second World War, there are no official record of the dome growth. But a local postmasters put a piece of paper on his window and periodically traced the shape, the profile of the dome, recording how it's grew. So this is for example, was the profile on 6 June, then after 8 months, and then this is the last record on 10 September 1945. And then to finish, I want to introduce you some effusive eruptions which I consider to be representative of the different kind of eruptive activity due to effusive eruptions. And I've chosen for Italy, I've chosen Etna 1669, that you maybe know, which was a very interesting eruptions, because it was the most destructive eruption of Italy. We changed the southeast flank of the volcano, and in general the south, reaching the city of Catania. It was a quite short eruption because it lasted only 4 months. But the eruptions, the altitude of the main vent, which were in Monte Rossi near Nicolosi, was at 800 meters above sea level, so it was a very low altitude vent. This eruption started on 11 March and covered the villages of Nicolosi, Malpasso, Montpellieri, Mascalucia, Mister Bianco, San Pietro Clarenza, but the most important thing was that it reached the city of Catania, that is 17 kilometers away from the vent, and this was due to the formation of, as I told you before, a complex lava tube. For this reason, it formed like a crust. So it formed these lava tubes, and then the event that is called ephemeral vent destroyed the city of Catania. Also, the lake and the river were buried, but in general, it was. It moved the coast of Catania, and with an area that is about 40 million square meters, with a volume which is very high, is 600 million cubic meters, with a peak of effusion rate that reached 640 cubic meters per second after 3 days. Lava was basically mafic in the first days, and then was more acid after the end, until from the second most to the end of the activity. This is on the left is a fresco by Giacinto Platania, which is in the Cathedral of Catania, which represented these eruptions, so the opening of the vent in Nicolosi, and then how the lava reaches Catania. And on the right, these are a reconstruction of the lava flows based on different field measurements done by some colleagues. Oh, another eruptions. I hope. Sorry. I have to switch off because video are not visible here. Okay, I have to share this. No. Okay. I don't have the final. Okay, doesn't matter. I will send you the slide to see the video. So another eruption is the sorry for for my pronunciation, Fagradalsfjall in Iceland in 2021. It was a very important eruption because they follow more than 1 year of earthquake activity and inflation deflation periods. And this was an eruption that even lasted few months, was the first eruption on the Reykjanes Peninsula after 800 of quiescence. The lava flow was erupted from a fissure that was long here on the top right. You can see the fissure, the main vents along the fissure, which was about 800 meters long. And it was characterized by different eruptive phases with the wind migration. So lava flow was first erupted from one vent, then from all these vents, then migrated to one. So it was a very a complex eruption. So obviously it was less dangerous than the one in the one of 1669, even if okay, in general, with respect to explosive eruptions, lava flows can be monitored. It is very unusual that people are killed by lava flows. On the contrary, they can be very the explosive eruptions and pyroclastic density currents can be very very dangerous for this from this point of view. And then another important eruption was in Kilauea in 2018. And this eruption was important because it was the second largest eruption in 500 years, after the Puo eruption that lasted 15 years. On the contrary, this eruption lasted only a few months, but was the most destructive. This is on the top right. You see the mapping of the final lava flow, which reached the sea and destroyed 723 buildings, which more than 3,000 residents evacuated, 2 major highways and 50 kilometers of public roads cut. So even if it was not dangerous for people to be killed, but they caused very important. They have important consequences for the local economy. It was a tube-fed Pao lava flow, which was produced by 24 different eruptive fissures, several hundred meters long, and reached the ocean after 20 days. Another characteristic of this eruption was that it was that Kilauea erupted in 2 different places, which is a quite uncommon phenomenon that had been happening for nearly a decade. At the summit, and with the huge emission of volcanic ash and also the collapse of the caldera, and this effusive activity due to eruptive fissures linked to the east rift zone of the Puo. The carbon call in Chile 2011. This was a volcanic eruption that for which we have a unique opportunity to make scientific observation of active rheolitic lava flow with the silica content higher than of about 70% of silica content, and this was an eruption that started on 4 June 2011 and occurred after about 50 years of inactivity of the volcano cordon col. But this was a very dangerous eruption because it started with the 15-kilometer high ash column, which was caused by very explosive eruption, which followed by an eruptive activity which was both effusive and explosive. As shown in figure on top, right top, this is the vent, and then the flow goes at the northern and the southern branch. But the most important thing is that formed about 90 breakouts from the lava flow emergence, with from the top you can see where the lava flow was still hot and was emitted starting from these 90 breakouts. These breakouts were important because they represented about the 12% of the lava plume of the lava volume, keeping the lava active many months after the effusion rate. Indeed, the eruption finished on 15 March 2012, but there were emission of lava even if until January 2013. Because the lava was hot and produced by these breakouts. So for this reason, it was a unique opportunity to make field observations of this very characteristic lava flow. And even also this eruption produced had important consequences on the economy of the region, because about 3,500 people were evacuated from the nearby areas, and the ash was so huge. The ash column was very important. Indeed, in 2 weeks, completed its first circle of all the Earth. So it was a very huge emission of ash. So it was very an important eruption, both from the effusive and the explosive activity. So for this reason, there was the stop of flights, international airlines, where international flights, even domestic flights, were cancelled. So there was it caused a travel chaos. And then I want to talk about finally about the hazard linked to lava dome, in particular the Soufriere Hills in Montserrat in 2003, which was the largest lava dome collapse in historical times from a volcano. It was the collapse occurred in about 18 hours between the 12th and the 13th July in 2003. And it was characterized by pyroclastic flows. Indeed, the Pelian lava dome complex collapsed, causing explosion and the pyroclastic density currents. This was preceded by an eruption, by an intermittent eruption since 1995, which was then followed by this major collapse that caused, as you can see from the MODIS image, which is a satellite images taken on 14 July, so the day after the end of the collapse. It caused a lot of material falling inside the sea. They traveled about 3 kilometers and reached the sea with a volume estimated of about 210 million cubic meters. An average velocity which was of 15 meters per second. So it was very 15 meters per second are not reached by lava flows or other eruptive products. The other link to these eruptions was the hydrovolcanic activity on the coast, which generated a violent inland directed pyroclastic surge. Then there was also a tsunami due to the fall of the material inside the sea, and there was also the materials caused by the dome collapse also caused the roof to collapse due to the weight of the material that accumulated on the roof of the building roof. Okay, I have finished my brief introduction of the on the lava flows and lava dome. I want to share your if you have some questions or I want to talk with you about your experience and what could be interesting for your for your work, obviously, regarding the lava flow. So we can have a brief discussion. This is an eruption from the southeast crater at Etna taken by one of my colleagues on 13 June 2022. Okay, I'll stop the